Welcome to our channel. Today discuss functions theorem. Very important theorems. First theorem. If f from capital A to capital B, g from capital B to capital C, are two bijections, then prove that G circle F whole inverse is equal to F inverse circle G inverse. Solution. Now start the solution. Given F from A to B is a bijection. So F from A to B is a bijection. So F inverse also bijection. Here F inverse mapping is B to A. Is also bijection. So the definition of the onto, that is, in this codomain, now take one element that is a small b belongs to capital B. Then there exit A belongs to capital A such that f of A is equal to B. This is that according to the definition of the onto from A to B. So f of A is equal to B. In this condition, A is equal to F inverse of B. Second one, here G from B to C is a bijection. G inverse also bijection. Here G inverse mapping is C to B is also bijection. So according to the definition of onto, function mapping is G from B to C. That is, in this codomain, now take one element that is small c. Small c belongs to capital C. Then there exit B belongs to capital B. Small b belongs to capital B such that G of B is equal to C. Here B is equal to G inverse of C. Here we can prove that G circle F whole inverse is equal to F inverse circle G inverse. So first here find the mapping of composite function G circle F. Here G circle F composite function mapping is A to C. This also bijection. So here G circle F whole inverse composite function mapping is C to A. This also bijection. Next, now take the mapping, the composite function F inverse circle G inverse. F inverse circle G inverse mapping is C to A. This also bijection. Now here observe G circle F whole inverse domain and also F inverse circle G inverse domain. Here G circle F whole inverse domain value is C. F inverse circle G inverse function domain also C. Here now observe G circle F whole inverse and F inverse circle G inverse domains are same. Since the domains of G circle F whole inverse and F inverse circle G inverse are same domain, that is a C. Same domain C. So here we can prove that G circle F whole inverse, G circle F whole inverse, common domain is C. So G circle F whole inverse is equal F inverse circle G inverse of C. Finally, we can prove that G circle F whole inverse of C is equal F inverse circle G inverse of C. In this common domain, now take the one element small c belongs to capital C. Already, according to the definition of the bijection G from B to C, here G of B is equal to C. So here clearly now take C is equal to G of B. C is equal to G of B. Here F from A to B is a bijection. According to the surjection definition, B is equal to what? F of A. So here B is replacing by F of A. F of A. According to composite function theorem, G of F of A is equal to G circle F of A. Clearly here C is equal to G circle F of A. So here A is equal to G circle F whole inverse of C. This is equation number 1. So RHS composite function value is here F inverse circle G inverse. Now take RHS composite function F inverse circle G inverse. Here common domain is C. So here now take F inverse circle G inverse of C is equal to F inverse of G inverse of C. According to surjection definition, G inverse of C is equal to what? B. So here G inverse of C is replacing by B. So F from A to B is a bijection. So according to surjection definition, F inverse of B is equal to what? A. So clearly F inverse circle G inverse of C is equal to A. This is equation number 2. From equation 1 and 2, G circle F whole inverse of C is equal to F inverse circle G inverse of C. C cancelled, we get the value G circle F whole inverse is equal to F inverse circle G inverse. Hence fruit. Okay. So here this diagram is for now take one set A, another set now take B, another set C. Clearly given data F from A to B is a bijection. So given F from A to B mapping is this one. F inverse mapping is B to A. And also G from B to C mapping is G from B to C. Here also G inverse mapping is C to B. Next composite function G circle F. G circle F mapping is A to C. This is F inverse. This is G inverse. And also this mapping is G circle F whole inverse. G circle F whole inverse is equal to C to A. And RHS composite function G F inverse circle G inverse. F inverse circle G inverse mapping also C to A. Okay. Once recall, given theorem is F from A to B, G from B to C are two bijections. Then prove that G circle F whole inverse is equal to F inverse circle G inverse. F from A to B is a bijection, so F inverse also bijection. F inverse mapping is B to A. According to surjection definition, F of A is equal to B, A is equal to F inverse B. J of B to C is a bijection, so G inverse is also bijection. So according to bijection, J of B is equal to C implies B is equal to G inverse of C. Composite function G circle F mapping is A to C, this also bijection. G circle F whole inverse mapping is C to A is also bijection. F inverse circle G inverse mapping is C to A, this also bijection. Now we observe G circle F whole inverse mapping is C to A. F inverse circle G inverse mapping also C to A. In these two composite functions, same domain. So that is the domains of G circle F whole inverse comma F inverse circle G inverse are same domain, that is a C. We can prove that G circle F whole inverse of C is equal to F inverse circle G inverse of C. So common domain C. In this domain, now take the one element C, small c, C belongs to capital C. Here given condition C is equal to G of B. Here B is equal to what? F of A. So here B is replacing by F of A. G of F of A is equal to G circle F of A. This equation can be expressed A is equal to G circle F whole inverse of C. This is take equation number 1. And in this problem, in this theorem, RHS composite function is F inverse circle G inverse. So here now take F inverse circle G inverse of C. Here F inverse circle G inverse of C can be written as F inverse of G inverse of C. G inverse of C is equal to here B. So F inverse of B is equal to here A. So F inverse of B is replacing by A. So F inverse circle G inverse of C is equal to A. This is equation number 2. From equation 1 and equation 2, G circle F whole inverse of C is equal to F inverse circle G inverse of C. C neglecting or cancelled. G circle F whole inverse is equal to F inverse circle G inverse. Okay, ends fruit. ఓకే, మీకు వీడియో నచ్చినట్లయితే లైక్ చేయండి, షేర్ చేయండి, సబ్స్క్రైబ్ చేసుకోండి. థ్యాంక్ యూ. Second theorem, if F from capital A to capital B, comma G from capital B to capital C, are two bijective functions, then prove that G circle F from capital A to C is a bijective function. Very, very important theorem for 7 marks in IPE examinations, that is annual examinations. Okay, listen, very easy. So you are given F from capital A to capital B is a bijective, function. F from A to B is a bijective function. Bijective nothing but F is a 1-1 function, and onto function, 1-1 function and onto function. So now take F from capital A to B is a 1-1 function. 1-1 function is known as injection. Here F from A to B is a 1-1. So the definition of 1-1 function, according to the definition of 1-1 function, let A1 comma A2 belongs to capital A, such that F of A1 is equal to F of A2 implies A1 is equal to A2. A1 is equal to A2. Here also F is a onto function. Take F from A to B is onto function, onto known as surjection function. So here now take small b belongs to codomain, that is a capital B. Small b belongs to capital B. Then there exits A belongs to capital A, such that F of A is equal to B. F of A is equal to B. Okay. F from A to B is a bijective function. That is F is 1-1 function and onto. In 1-1 function, now take A1 comma A2 belongs to capital A, such that F of A1 is equal to F of A2 implies A1 is equal to A2. F from A to B is onto for small b belongs to capital B. Then there exists A belongs to capital A, small a belongs to capital A, such that F of A is equal to B. Another function given G from B to C, is a bijective function. Bijective function nothing but G is a 1-1 function and also onto function.
First we take g from b to c is a 1-1 function. 1-1 function is nothing but injection, is known as injection. Another name is injection. So here in this domain, now take the two element small b1 comma small b2 belongs to capital B, such that here function is g. So g of b1 is equal to g of b2 implies b1 is equal to b2. b1 is equal to b2. Now take g is a onto function. G from b to c is onto function. Onto is known as surjection. So in this codomain, capital C, here now take one element, small c belongs to capital C. Then there exits in this domain, now take one element, small b belongs to capital B, such that your function is g. In this domain, now take the one element small b, so g of b is equal, in this codomain, now take the one element small c, so here g of b is equal to c. G of b is equal to c. Okay, finally we prove that, G circle f from capital A to C is a bijective. Function. Bijective means bijection. We can prove G circle f from capital A to C is a bijective. First we prove G circle f from capital A to capital C is a 1-1 function, that is injection. We can prove that G circle f from capital A to capital C is a 1-1. In this domain, now take two elements, small a1 comma small a2 belongs to capital A. So here now take G circle, the function is G circle f. So here now take G circle f of a1 is equal to G circle f of a2. We can prove that a1 is equal to a2. According to composite function definition, G circle f of a1 can be written as G of f of a1. Here also can be written as G of f of a2. Okay, clearly here f of a1 now treated to small b1, f of a2 now treated to small b2. This is in the form of G of b1 is equal to G of b2. Clearly here G is a 1-1 function. According to 1-1-1 function definition, G of b1 is equal to G of b2 implies b1 is equal to b2. Here b1 nothing but f of a1, b2 nothing but f of a2. Clearly here G is a 1-1 function. G is a 1-1 function. And also f also 1-1 function. According to definition 1-1 function, f of a1 is equal to f of a2 implies a1 is equal to a2. Clearly here G circle f of a1 is equal to G circle f of a2. Here a1 is equal to a2. So G circle f from capital A to C is a 1-1 function. Next we can prove that G circle f from capital A to C is onto. That means surjection. We can prove that surjection. Okay. In this codomain, now take the one element, small c belongs to capital C. Here now take small c is equal to G of b. Clearly here G is a onto function, so G of b is equal to c. So here c is equal to G of b. F is onto function. According to the definition of onto, clearly B is equal to what, Nana? F of A. So here B is replaced by F of A. Okay. So G of F of A can be written as G circle F of A. G circle F of A. So therefore C is equal G circle F of A. According to onto definition, that is for C belongs to small c belongs to capital C, then their exit A belongs to small a belongs to capital A, such that G circle F of A is equal to C. G circle F of A is equal to C. So G circle F from capital A to C is onto function. So given composite function G circle F is one function and also onto function. So given G circle F from A to C is a bijection. Because given composite function satisfy the conditions one function and also onto. So G circle F from A to C is a bijection. Okay. Take screenshot. Very important. ఓకే, మీకు వీడియో నచ్చినట్లయితే లైక్ చేయండి, షేర్ చేయండి, సబ్స్క్రైబ్ చేయండి, మీ ఫ్రెండ్స్కి షేర్ చేయండి. థ్యాంక్ యూ.
Next problem. Let f is equal the set of 1 comma a comma 2 comma c 4 comma d 3 comma b and g inverse the set of the elements 2 comma a comma 4 comma b 1 comma c 3 comma d. Then prove that G circle F whole inverse is equal F inverse circle G inverse. Okay. మనకు కాంపోజిట్ ఫంక్షన్ బేస్ చేసుకుని G సర్కిల్ F హోల్ ఇన్వర్స్ ఇస్ ఈక్వల్ F ఇన్వర్స్ సర్కిల్ G ఇన్వర్స్ థీరం ఇవ్వడానికి ఛాన్స్ ఉంది. థీరంకు ఆల్టర్నేట్ ప్రాబ్లం ఇవ్వడానికి కూడా ఛాన్స్ ఉంది. థీరం ఇంపార్టెంట్ అండ్ ఆల్సో ప్రాబ్లం ఆల్సో ఇంపార్టెంట్. ఓకే, గివెన్ F is equal 1 comma a 2 comma c 4 comma d 3 comma b. Okay, so here in this function, that is f of 1 value is a, f of 1 value is a, f of 2 value is c, f of 2 value is c, f of 4 value is d, f of 4 value is d, f of 3 value is b, f of 3 value is b, according to the mapping of the given function f. Here f inverse mapping is domains and codomains are interchanged. That is a comma 1, here c comma 2, here d comma 4, b comma 3. That is here function mapping is f inverse of a value is 1, here f inverse of c value is 2, f inverse of d value is 4, f inverse of b value is 3, f inverse of b value is 3. Second function mapping is given hypothesis G inverse is equal to the set of 2 comma a 4 comma b 1 comma c 3 comma d. That is here G inverse of 2 value is a, G inverse of 4 value is b, G inverse of 1 value is c, G inverse of 3 value is d, according to the mapping of the G inverse. Okay, here G is equal mapping is in this G inverse function domain and codomain are interchanged. So 2 comma a can be changed to a comma 2. Here changing is b comma 4. Here changing is c comma 1. Here value is d comma 3. Okay. Here g of a value is 2, g of b value is 4, g of c value is 1, g of d value is 3. Here we can prove that G circle F whole inverse is equal to F inverse circle G inverse. First, here we can prove that, G circle F whole inverse is equal to F inverse circle G inverse. Okay. Now take the value. First we find G circle F of 1. G circle F of 1. Okay. Here G of F of 1. Clearly here G of 1 value is, F of 1 value is A. So here F of 1 value is A. F of 1 value is A. So F of 1 is replacing by A. Here G of A value is 2. G of A value is 2. Next now take G circle F of 2. Okay. In this function F, domain value is 1, 2, 3, 4. Here also, now take the values G circle F of 2. G of F of 2. Here F of 2 value is C. G of C. G of C value is 1. G of C value is 1. Next we calculate the value G circle F of 3. G circle F of 3 value is G of F of 3. Here F of 3 value is B. F of 3 value is B. So G of B. Clearly G of 4 value is, G of B value is 4. Next calculate the value G circle F of 4. G circle F of 4 can be written as G of F of 4. Here F of 4 value is D. F of 4 value is D. So here G of D. G of D value is 3. So is equal to 3. So here G circle F is equal to the set of the elements 1, 2. One input is the output 2. Here mapping is 2, 1, 2, 1, 3, 4, 4, 3. Here LHS is G circle F whole inverse. Here now find G circle F whole inverse. Given function mapping is 2, 1, 1, 2, 4, 3, 3, 4. Just interchange. Domains and codomains are interchange. Okay, this is equation number 1. Here RHS we can prove that F inverse circle G inverse. So we calculate the values F inverse circle G inverse of 1. Okay. F inverse circle G inverse of 1 can be written as F inverse of G inverse of 1. Here G inverse of 1 value is C. So G inverse of 1 value is C. So F inverse of C is equal to what, Nana? 2. This value is 2. Next calculate the value F inverse G inverse of 2. This is equal to F inverse of G inverse of 2. In this problem, G inverse of 2 value is A. So G inverse of 2 value is A. So here F inverse of A is equal to value is 1. So here value is 1. Next, F inverse circle G inverse of 2 is equal F inverse of G inverse of 2. G inverse of 2 is equal value is A. So F inverse of A value is 1. So here value is 1. Next calculate the value F inverse circle G inverse of 3. Here F inverse of G inverse of 3 is equal. Here G inverse of 3 value is D. So here F inverse of G inverse of 3 value is D. So F inverse G inverse of 3 is replacing by D. So F inverse of D is equal to how much? 4. So F inverse circle G inverse of 3 is equal to F inverse of G inverse of 3 is equal F inverse of D. F inverse of D is equal to value is 4. Next value F inverse circle G inverse of 4 is equal F inverse of G inverse of 4. Here G inverse of 4 is equal to value is B. So here G inverse of 4 is replacing by B. F inverse of B. F inverse of B is equal to what, Nana? 3. So here value is 3. Here value is 3. So given composite function mapping is F inverse circle G inverse is equal 1, 2. Next 2, 1. Next 3, 4. 4, 3. This is equation number 2. From equation 1 and 2, 1 and 2 both are equal. So therefore G circle F whole inverse is equal F inverse circle G inverse. Hence Freud. Okay, thank you. మీకు వీడియో నచ్చినట్లయితే లైక్ చేయండి, షేర్ చేయండి, సబ్స్క్రైబ్ చేయండి, మీ ఫ్రెండ్స్కి షేర్ చేయండి. థ్యాంక్ యూ.